Okay, so hello once again. This time we're going to discuss a problem associated with orthogonal sets and coordinates. And well, to make an exploration, we start like this. Let the collection U1, U2, U3 be a set of orthogonal vectors in a Euclidean space, something that looks like Rn. And suppose that W is in the span of this set, where we have the following three conditions, right? And well, we also have information associated with the orthogonal vector itself. We need to find the unique coefficients a1, a2, and a3 such that W is described as a linear combination of those elements u1, u2, and u3. This is what we call the coordinates of W with respect to u1, u2, and u3, and in that order. Right? So let's start. First, from the orthogonality of the set, we have this. For each I and j in this range, with I different from j, we have that ui transpose uj is equal to 0. That's exactly just bringing the definition of an orthogonal set. Right? Well, recall that u1, u2, and u3 being an orthogonal set is also linearly independent. Okay? There will be a subsequent video where we mention this connection explicitly. So it forms a basis of its span space. Also, the coefficients a1, a2, a3 exist. Well, now that we have a basis, right, we can perform a series of row reduction processes just like the ones that we have been doing several times. But, well, that's probably not what we want to do here, because we have other type of information that we can use. In other words, at the very end, we just need to find these numbers. Well, how? I'm going to start like this. Write W exactly in that fashion: A1, U1, plus A2, U2, plus A3, U3. So you would say that A1 is the coordinate of W in the direction of U1, A2 is the coordinate of W in the direction of U2, and A3 is the coordinate of W in the direction of U3. I'm going to label this equation just to make it available. And, well, now we're going to do one thing. We're going to multiply this equation on the left by the transpose of U1. Why? Because it seems like we have to use the information that is here available for us. So let's do that. So we want to multiply on both sides of this equation by U1 transpose. To get, well, to get this, U1 transpose W is equal to U1 transpose times A1 U1 plus A2 U2 plus A3 U3. And from here, well, we're going to make use of the distributive property, and we have and also properties of the scalar product to rewrite this equation in this fashion as A1 U1 transpose U1 plus A2 U1 transpose U2 plus A3 U1 transpose U3. But then, look, the set of vectors that I'm underlined here is orthogonal. So, these are 0. Well, that means that this is nothing else but A1 U1 transpose U1. Well, from here, we get that also U1 transpose W is equal to A1 U1 transpose U1. Then A1 is equal to U1 transpose W over U1 transpose U1. Why is that we are allowed to do this manipulation? Well, because now we're just dealing with numbers. These are just 1 by 1 matrices, if you want to see it that way. And this results in 2 over 5. Similarly, we can get that U2 transpose W is equal to A2 U2 transpose U2, and U3 transpose W is equal to A3 U3 transpose U3 by multiplying equation 1 by, well, not by, well, multiplying equation 1 on the left by U transpose 2 and U transpose 3 respectively. So A2 is equal, based on a similar manipulation, right, like this one, to U2 transpose W over U2 transpose U2, which is 4 over 7, and A3 being U3 transpose W over U3 transpose U3, which is 8 over 9. Well, and with this we finish. I hope that you like it. Take care.